In section 8.3, we continue learning about hypothesis testing that we've been exploring the last few videos. So what you're going to see is a very familiar flow of how we approach hypothesis testing. The big difference is the last four examples we looked at were all about a single proportion, a percentage. And in this video, we're going to look at two examples, and then I'll do another two examples in my video after this, all related about a single mean or a single average. So let's see how the major flow doesn't really change. There's some minor details that we'll make some adjustments along the way, but you'll pick those up. Again, our calculator is going to be our best friend when it comes to getting the final numbers. Again, no formulas. Let's learn how to knock this one out. So here's the claim. The opening sentence says, back in 2015, the annual miles driven per vehicle was 10,300 miles. I believe it's more now. Step one, set up the null and alternative hypotheses. The big theme here is we're now shifting from proportions to means. So the average miles driven, I think annually is 10,300 for all vehicles, let's say in the United States. So average instead of proportion says mu, not p. So in both statements, we're going to use the population symbol for mean, which is mu. So let's see. There's this claim that it was it was known to be 10,300. If I believe it's more now, what does more than 10,300 look like? It looks like the greater than symbol. Doesn't include the equal sign. The complement of this, my null, would be less than or equal to, but we've learned we can get by with just saying equals every time for the null. Okay, that's how all hypothesis tests start. Well, the second thing we need is we need some data. We need some evidence. And this will propel us forward. So I'm going to give you some numbers. Let's say a sample of 20 randomly selected cars were looked at. And in the last year, the average miles driven for those 20 cars, let's say, was 12,346. And the standard deviation of those 20 cars was 3,490. And let's go with an alpha level of 5%. Again, that's where we make our decision at the end. That doesn't do anything right now. So again, this claim is about all vehicles in the United States, that the average amount driven is over 10,000 miles. I randomly selected 20 cars, and their average was 12,000. Does this support my alternative so far? Yes, it does. That always should be true right now. My sample mean is greater than this. Is that enough evidence to say that the population mean is 10,000? I don't know yet. Let's find out. So, last videos we built a normal curve, and this is almost is one. Let me tell you, this time, whenever we're working with means, this is what is called a T-curve. Very similar to a normal curve. You're not going to really think much different about it, but just so you know, there is something called a T-curve when the data is built around averages, not proportions. One thing I like to do on my sketches, there is a concept called degrees of freedom that helps remember this is related to something called a T-curve. The degrees of freedom is simply the sample size minus 1. 20 minus 1, 19. And so that reminds me this is a T-curve. The other thing I like to put on my sketch is I like to label what is on the top number line. We are capturing averages or means. And my second number line is my test statistic. In the world of proportions, it's a Z number line. In the world of means, it's the T number line. So, what was true last time is true still. How do I set up my number line? My null number always sits in the middle, so I go up and I grab 10,300. And then my evidence, 12,000, clearly is to the right of that, somewhere to the right. I don't know if it's close or far away. This is a one-tailed test because it's just greater than, so we are out to find the area under this curve, which is called the p-value. So I'm missing a couple of things right here, which is when we go to my calculator. So like the world of proportions, the steps to get there, you're going to hit Stat, go over to the Tests menu, but this time, instead of choice 5, it's choice 2 for something called a t-test. Choice 5 is the one proportion z-test. And so again, in the title itself, it reminds you what kind of test statistic you're getting. Proportions give you z's, means give you t's. So let me put this in. Calculator on, stat test number 2 for t-test. So let's see what we've got. Again, right off the bat, it's asking what is the null, and notice the symbol for mu, and that's my 10,300. My sample mean, 12,346. My sample standard deviation, my sample size, and finally my alternative, which is a greater than. We head to calculate, and here's some numbers. Some we know, some we don't. You'll see the numbers you've inputted. The two new numbers on this screen are my test statistic and my p-value, the t-score and the p-value. So I can see what those are. My t-score is 2.62. The p-values is the monster in the room. That's going to make all the decisions for us. So 0.0084. Let's write that down. Again, that's what this area is. My p-value is 0.0084. So that's very tiny. There's hardly anything there. So visually, I drew that tail much bigger than it should be. If it was more accurate, I would have made it even further down here. You would hardly see anything shaded. But what does that mean? When your evidence is so far away from your null, that means we have strong evidence that the null probably is not true. And this is how we write it up. We first say my decision is reject the null since my p-value is less than my alpha level that we gave at the top. So what's my conclusion? We have strong evidence the annual miles driven for all cars is more than 10,300. Good. All right, let's take a look at a second example and we'll call it good. Okay, so we'll go a little faster this time because we now have seen this setup. So let's check out what's going on here. Second example says the average number of siblings that a student at Butte College has is more than 3. Okay, well, the word average is clearly screaming at us. So as I set up my null and alternative statements, average says mu greater than 3. Again, we use the population symbol because we're saying the average for all students would be more than 3 siblings. The complement to that would be less than or equal to, but we'll just say this. One thing I want you to see this time is let's work with some real data. These numbers came from an actual class, statistics class I taught a couple of semesters ago, how many siblings each of those students had. And so, as you know to do, if I were to head to my calculator, stat, go to edit, head to list 1, you'll see that I've already entered those numbers into list 1. You should know how to do that. When I return to my home screen, we'll run one var stats by hitting stat calc number 1 of list 1. And there's my data. So I had to do it myself this time. So let me jot down the important numbers here. My sample size was 28. The sample number of siblings, we'll just call that 3.3, and my standard deviation 2.0915. All right. So like I always say, at this stage, does my evidence support my alternative right now? Yes. It looks like the average for this sample of students is greater than 3. Is that enough to say that the average of all students is greater than 3? We don't know. And that's why we need the next few steps. So off to my sketch. Again, a bell-shaped curve. Is this a normal curve? No, it is not. It's a close cousin called a T-curve. Let's see if you can tell me the degrees of freedom before I write it down. Has something to do with this sample size. So I think my degrees of freedom would be 27. Always one less than the sample size. I like to label means. T is the test statistic. Right down the middle is my null, 3. My sample mean then falls to the right. Put it over here. Again, this is just a one-tailed test. Looks like I need a couple more numbers, and this is when I go to my calculator to get my last two numbers, my test statistic T and my p-value. What's nice is when you're given real data and you run one var stats, notice this. Stat test number 2. You have to control, notice there's my old null from the first example we did, so I do have to change that. The calculator doesn't know what the problem is we're working with, so I tell it 3. But notice as a gift, because we ran one var stat, my mean and my standard deviations are already sitting there. And we don't have to make any rounding decisions, so just leave those alone. My sample size has been upgraded. All I have to do is, again, change my null, make sure my alternative is the correct one, which it is, and then off to calculate. So I will jot down my test statistic to 2 decimal places, so 0.81. My p-value, again, is the area of this tail, 2.116. So again, I didn't write it at the top. Maybe I, again, should make it very clear. Let's say my alpha level is 0.05, the usual. So I can make a decision right now. This time I'll start by noticing since my p-value is greater than my alpha level, the decision is fail to reject the null. And again, why that is, that 21% means this tail has a large area, which means this 3.3 is much closer to the 3 than we would want it to be. In other words, could the average still be 3, even though the sample average was 3.3? Yeah, that's not extreme enough. That 3.3 wasn't way deep into this tail. It was close enough to this 3 that, it could still be 3. And that's our conclusion. That's what it means to fail to reject the null. We'll say we have weak or insufficient evidence to support the alternative. Which means it could be true. The average number of siblings is just 3, not more than 3.